so that the ensemble spread is an intrinsic property of the simulated climate. These large ensembles have been developed to better quantify the internal climate variability relative to the forced climate change. So today we'll hear two presentations related to the application of these large ensembles in Arctic research. And so our first presenter is Marika Holland. Marika is the head of the Paleo and Polar Climate section at the NSF National Center for Atmospheric Research in Boulder, Colorado. And the title of her talk is The Influence of Historical Forcing Uncertainty on Simulated Arctic Change. Marika?
Thanks. So I'm going to share my screen. Hopefully this works.
Yeah.
All right. So thanks. Thanks to all of you for being here and for IARPIC for having me. So yeah, as Rich mentioned, I'm going to talk about the influence of historical forcing uncertainty on simulated Arctic change. And I'll just note that this work, a lot of the plots I'm going to be showing, et cetera, were recently published in this manuscript. And so you can find a link to that here at the bottom of the page. So when we think about uncertainty in our climate simulations, and in particular, I'm talking about historical climate simulations here, we often consider the role of internal variability. So large ensembles have been very useful at allowing us to quantify that impact of internal variability. So this just shows one example of this. This is from the CESM1 large ensemble, and you can see the histogram of September extent decadal trends for two different time periods. So I'm not going to go into any detail here, but you can see that there's a large spread in decadal trends that are simulated in this model system. And that's a result of the internal variability, the chaotic nature of the climate system. It's also well understood that model structural differences lead to uncertainty in our climate simulations. And so this results from the fact that we have different parameterizations, different resolution, et cetera, in our climate models. And so the example I'm showing here of this shows the September Arctic sea ice sensitivity metric. So this is the change in September ice area per change in global mean surface temperature from two different large ensembles, the CESM1 large ensemble and the CESM2 large ensemble. So you can see the spread across the ensemble members that's associated with internal variability, but you also see that these two sets are somewhat distinct. There's a different distribution of this sea ice sensitivity metric, and you might attribute that purely to model structure. And I'll show you why you would be wrong in doing that. Because there's another source of uncertainty that is somewhat less appreciated. And that's the fact that the historical forcing that we use to drive our historical simulations is also uncertain. So what I'm showing here is the global mean anthropogenic aerosols from emissions from a number of different aerosols. And you can see that in the historical period, which is the period to the left of that blue line, different forcings were used in CMIP5 versus CMIP6. And this is because those forcings are uncertain. We don't have observations of all of the sources of emissions, et cetera, back through the 20th century. So these emission sources are uncertain. We use different forcings across different CMIP generations, and that represents some of the uncertainty that we have in what these actual aerosol emissions are. This is also true for volcanic emissions, which I'm not showing here, but it's also the case for those emissions as well. So we wanted to address the question of what is the influence of model structure and forcing uncertainty on historical Arctic change. And so in this work, I'm just going to focus on the forced climate signal. So I'll quantify that using ensemble means from these large ensembles. And I'm only going to do this within the context of two models, the CESM2 model and the CESM1 model, and the uncertainty that's inherent in the CMIP6 versus CMIP5 forcings. So we're using large ensembles for this. Rich introduced what these are. These are a large number of simulations from a single climate model that are all subject to the same external forcings, but they have small perturbations in their initial state. And then because the system is chaotic, they have different trajectories over time. So we can look at the forced response from these. This is going to be mostly anthropogenic by looking at the ensemble mean of those simulations. So that averages out the internal variability noise and leaves us with a force signal. We can also, of course, look at internal variability, which is the variations about that ensemble mean. And the change over time in these simulations is, of course, a combination of the two. But for this work, I'm really just going to look at the forced response. And I can very well quantify that forced response because I have large ensembles. So the experiments that I'm using are the CESM1 large ensemble that has 40 ensemble members. Those members are run with the CMIP5 forcings. And then the CESM2 large ensemble, where I have 50 ensemble members run with the CMIP6 forcings. These models, the CESM1 and 2, they differ across all their components. They have different climate sensitivity, different climate feedbacks, and more. So they are quite different models. But we can't disentangle from those two large ensembles the role of model structure and model forcing because they have differences in both. And so we've run this new set of simulation, 15 ensemble members that we're referring to as the CESM2 CMIP5 runs. These have the new model, but the older CMIP5 forcings. And so using these, we can now attribute differences between the CESM1 large ensemble and the CESM2 large ensemble to the role of model structural differences versus model forcing differences. We have another set of simulations. I'm not going to talk about these in much detail, but just so people are aware that we have these. These are also part of the CESM2 large ensemble. There's 50 ensemble members. They use the CMIP6 forcings, but for the latter part of the historical record, they have smooth biomass burning emissions. And so this was done because in work by Patricia Durrett-Pentini and others, it was found that changes in the variability of the biomass burning affected the Arctic climate in particular. So those runs are available. I will show some results from them, but I'm not going to talk about them in much detail. So using this set of runs, we can attribute differences between the CESM2 large ensemble and the CESM1 large ensemble to model uncertainty, forcing uncertainty, and then this aspect of uncertainty associated with variable biomass burning emissions. Okay, so what does this look like? So I'm showing here the air temperature change for the first couple decades of the 21st century minus an early period of the 20th century. So this is more or less a 100-century timescale change in surface air temperature. This is from the CESM2 large ensemble, and you can see the kind of classic picture of Arctic amplification there. And this shows the difference in that warming in CESM2 minus CESM1. So the CESM2 large ensemble has increased warming in the high northern latitudes, and it has other changes across the globe that are also quite interesting. For example, a reduced warming in most of the Southern Ocean. So again, the model structure and model forcing is different here. So now we can use these new simulations to attribute that difference in the CESM2 large ensemble and CESM1 large ensemble to model structural differences, which is shown on the lower left, and model forcing differences, which is shown on the lower right. And if we're just thinking about looking at the Arctic response here, we see that this increased warming in the Arctic is really due to model forcing. It is not due to the difference in the CESM2 versus the CESM1 model. It's instead due to the CMIP6 versus CMIP5 forcing differences. And the model structure actually counteracts that somewhat. So we can look at other aspects of the changing Arctic. So this shows September Arctic sea ice cover. You can see that the CESM1 large ensemble, which is shown in the red line here, has more sea ice in the Arctic over all time periods than the CESM2 model, which is the large ensemble is shown in black here. So there's more sea ice in CESM1 than in CESM2 large ensembles, but the rate of ice loss also differs across these simulations. So again, we can attribute this to the difference in model structure and model forcing. And so you can see here that the model structure, shown on the right panel in black, is responsible for this difference in the mean state. So less ice in CESM2 is a consequence of model structure. The model forcing has actually limited impact until about 1990. And then the model forcing, the CMIP6 forcing relative to the CMIP5 forcing, drives increased sea ice loss over the late historical period. And that's consistent with that forcing driving additional warming in the Arctic as well. So if we go back to this sea ice sensitivity plot, looking at the CESM2 large ensemble in the black here and the CESM1 large ensemble in the gold, you might look at this and say, well, the CESM2 model has a better sea ice sensitivity relative to observations. It's a more sensitive and more larger sea ice loss relative to the global mean surface temperature change. However, if we now include these simulations that use the new model, but the old forcings, we find that if we use the same forcing, the difference between the CESM1 and CESM2 model is quite minimal. And if anything, the CESM2 model is less sensitive if we use the same forcing as what was used in the CESM1 simulations. So another aspect that's interesting in terms of the Arctic change signal is the surface albedo feedback in this early part of the 21st century. So what you're looking at here is the difference in the surface albedo feedback in the CESM2 large ensemble minus the CESM1 large ensemble. So the CESM2 large ensemble has a weaker albedo feedback, and that happens despite the fact that the CESM2 large ensemble has more sea ice loss. So that's very counterintuitive. If we look again at the influence of model structure on the top here versus model forcing in this difference, we find that it's really associated with model structural differences between the CESM2 and CESM1 model. And model forcing is playing a limited but somewhat counteracting role. And recall that model structure affected the mean ice area, but had little influence on the sea ice area loss in the late historical period. So we can, dig a little bit more deeply in terms of this counterintuitive result, and reflect on the fact that the surface albedo response is associated with both changes in ice area and changes in ice albedo. So the changes in ice area are not what's driving this difference between the surface albedo feedback in the CESM2 versus CESM1 large ensembles. So instead, it must be associated with this changes in the surface albedo itself. And we see evidence that there's a possibly important role for the snow climatology here. So this is some work from Melinda Webster. I'm looking at the snow in the CESM1 large ensemble on the left and the CESM2 large ensemble on the right. And this shows that the CESM2 large ensemble has thinner snow, a longer snow-free season. That lower snow cover results in a lower surface albedo. And having a lower surface albedo in the historical period gives us less capacity for albedo change due to snow cover changes. And this is what contributes to that weaker surface albedo feedback in the CESM2 large ensemble. So to summarize, historical forcing uncertainty is sizable. It was actually much more sizable than I was expecting in this case. And it complicates the comparison of simulations across CMIP generations because the forcing is updated with new CMIP simulations. It also complicates the comparison with observations. For the historical period, the CESM2 large ensemble has larger Arctic warming and ice loss than the CESM1 large ensemble. This is due to the influence of the CMIP6 forcing relative to the CMIP5 forcing. And it's somewhat counteracted by differences in the model structure between CESM2 and CESM1. The CESM2 large ensemble has a weaker surface albedo feedback, despite the fact that it has larger ice area loss in this early 21st century time period. And this results from model structural differences, and there's a strong evidence that it's related to the snow on sea ice climatology. I do want to emphasize there's lots of things that are unanswered in terms of the Arctic climate change in these simulations. And I want to make clear that these simulations are fully available and publicly available, and we really encourage other people to use them to disentangle some of these questions on the changing Arctic climate. And so those simulations and how to find them can be found in this reference here at the top, and the other work that I've mentioned is also the references for those are shown here as well. So I think we're taking questions at the end. Okay, so I'll just show you my nice polar bear and hand it back to Rich. So thanks, everyone.
Thanks very much, Marika. That was excellent. So you can ask a question by raising your hand, and this app is always changing. I think the raise your hand button is under the react button. Yes. So you can do that, or you could unmute, or just otherwise get our attention. So Marika, I guess there's a question. The forcing values, I would assume, evolve due to enhanced information, better reconstructions of past forcing conditions. So would you have any advice then for CMIP7 then? Should they aim more towards consistency, or should they try to improve their forcings with time? I don't think that CMIP has tried to have consistency in the past, right? We've gone from RCPs to SSPs for the forcing scenarios. So do you have any thoughts about what they should do?
So that's a hard question. I do think,
Sorry.
I mean, I think as we have better observations and more information on historical forcing, where we should be able to know what the historical forcing was, because it has already occurred, that it's useful to update our forcings and get a better forced simulation of the climate system. But I think we need to use a lot of caution then when we compare across CMIP generations. I also think that there are sometimes choices made that might improve the forcings, but have unintended consequences. And a good example of this is the biomass burning emissions. And I point you to Patricia's paper that is in my reference list on this. So there are satellite estimates of biomass burning emissions back to 1997. And so for CMIP6, it was decided to use those in the biomass burning emissions. But prior to 1997, we have much more limited information. And so the variability actually changed between the biomass burning emissions prior to 1997 versus after that. It's better data after 1997, but that change in variability has an impact because there's nonlinear cloud aerosol interactions that happen in the Arctic. So what the right choice is there? I mean, either you need to add some sort of variability, which you don't actually know prior to that 1997 period, or smooth your estimates of biomass burning after 1997, which means you're making those emissions less realistic. But they have unintended consequences. And so we need to think through those kinds of questions in how we force our models. So, but it's a hard question, honestly.
Yeah. How long you have your hand raised?
Do we have time for a question now? Or?
Sure, go ahead.
Thanks, Marika. I wonder if you looked at the sea ice surface albedo change or snow change, if that's related to the new biomass emissions for CMIP6?
So we haven't looked at, so we do see that the surface albedo change is less in the CESM2 large ensemble than the CESM1 large ensemble. And that appears to be associated with the snow climatology and the fact that you have low snow cover and that starts out with sort of a lower albedo. And so changes in the snow cover are less impactful in CESM2 than in CESM1. But I will say we definitely need to do more work on this. This isn't in the paper that I mentioned. I mean, we show the metric of the albedo feedback, but there are other possible candidates as well, like changes in pond cover, changes in the black carbon forcing of the surface albedo itself. And Patricia did look at that a little bit in her paper and found minimal evidence that that was having a big role. But there's definitely a lot more to do. And so again, I'd encourage people, if they're interested, you know, make use of these simulations.
Great, thank you very much.
Okay, there were a couple of comments in the chat. Vladimir Alexeyev wrote, each new set of runs adds more choices for scenarios. How do we navigate it when using your large ensemble runs? Do you have any general response to that, Marika?
Well, I think, yeah, I mean, it's complicated. And I think that, you know, there's value in doing runs with older forcings, even with a new model, as we've done here, because it allows you to disentangle the kind of relative role of model structural and forcing uncertainty. Our large ensembles that we run, we always, for the future simulations, we always pick a single scenario. And so, you know, our CESM1 large ensemble used the RCP 8.5, our CESM2 large ensemble used the SSP 370. So there's differences in the future forcing there as well. The simulations I mentioned here with the CESM2 and CMIP5 forcing allow you also to look at that future forcing and disentangle the role of model structure versus model forcing differences, where in that case, you have very big scenario forcing differences. So these models run through the 21st century and allow you to look at that as well.
Okay.
Yeah.
And then Amanda Lynch writes, this problem highlights the conflict between modeling for policy and modeling for science. I think that's exactly what is going on here. Would you have a response to her comment?
Yeah, I mean, I think you're right. And I think, you know, when we're thinking about, you know, near-term projections and things of that nature, where there's a lot of interest in these from a policy perspective, there's value in doing things like initialized predictions with our models, even on decadal timescales. But how we get the best simulation of both the historical climate to try and understand the changes that have occurred over the historical record, and also so that our models are starting from a reasonable initial place to look at future projections, is challenging given these uncertainties that we have in things like the forcings. So, and Amanda, I'm not sure if that's exactly what you meant in your comment, but yeah.
Okay. I was just thinking here. When you ran for CMIP5 forcing, so my understanding of CESM2 is that it has two-moment cloud microphysics, and CESM1 does not. Is that correct?
I think that's right.
Okay.
So we have different modal aerosol schemes as well, and so exactly. So we have to make choices in terms of how the aerosol emissions were spread across the modal aerosol treatment.
I guess my question was, I think the forcings have also evolved because the Earth system models have been able to represent more things and have added forcings. So were you able to have all of the forcings required for CESM2 when you ran for CMIP5, or was that an issue?
No, we had all the forcings that we needed.
Okay.
Yep. It's more the choice of how they get distributed in kind of the modal aerosol treatment, but that's, but we have the forcings available. So yeah.
Okay. All right. Thanks very much. So let's go on to our next speaker. And that is Tyler Janoski. Tyler is a postdoctoral fellow with the NOAA National Severe Storms Laboratory and City College of New York. And the title of his presentation is Ultrafast Arctic Amplification, Insights from a Large Ensemble of CESM Simulations.
Thank you for the introduction. Let me just share my screen.
Okay.
Yeah, sorry, just gonna hide the annoying meeting controls.
Yeah, good.
So, my name is Tyler, and I'm going to be talking about some work that I did when I was at Columbia University. Now, given that this is an aerobic talk, I anticipate that many people are familiar already with polar amplification, but just as a reminder, like Marika showed earlier, Arctic amplification or polar amplification is an amplified surface temperature response to some type of climate forcing. In the plot on the right, I show the surface air temperature response some number of years after you quadruple the amount of CO2 in a collection of CMIP5 models. And you can see that strong latitudinal gradient present in the Northern Hemisphere, not so much present in the Southern Hemisphere. So often when we're thinking of polar amplification in the context of our modern climate, we're thinking of enhanced Arctic warming with increasing greenhouse gas concentrations in our atmosphere. Over the past few decades, the Arctic has warmed between 2 and 4 times more than the global average. That depends very much on the source that you go to for that amount. And what makes this topic so interesting is there is a ton of debate about its causes. Aside from being an interesting scientific question, it's difficult to produce an accurate or well-constrained, precise projection of what the future Arctic is going to look like when you don't have a complete understanding of the mechanisms that are causing this alarmingly fast temperature change. Past studies have identified many potential causes of Arctic amplification, starting with the radiative forcing, something like the radiative forcing from increasing CO2 concentrations in the atmosphere may not necessarily affect every latitude in the same way. And in the case of CO2, it does not. So the radiative forcing itself can potentially cause Arctic amplification. Another potential culprit are feedbacks, which enhance or diminish an initial temperature response to the forcing. I highlight some of those in the plot on the left that I've looked at, like the surface albedo feedback, cloud feedbacks, water vapor feedback, and the Plancke lapse rate feedbacks, which are different flavors of temperature feedbacks. Lastly, there can also be changes in the amount of energy or heat brought into the Arctic by the atmosphere or ocean, and depending on the sign of those changes, those can potentially cause or oppose Arctic amplification. Now, there are tens of studies on Arctic amplification that attempt to attribute the amplification to a specific mechanism or a combination of mechanisms or feedbacks. But what you'll find if you give a even cursory look over them is that they reach very different conclusions. What I found when I first approached this topic was that the majority of studies focused on this time-averaged quasi-equilibrium response to radiative forcing. What I mean by that is that it's common to look at the mechanisms of Arctic amplification, say 100 or more years after you increase CO2 in some climate model simulations. By that point, summer sea ice is gone in the Arctic, the stability of the atmosphere is very different. And while those studies are helpful, Arctic amplification is not only a time average quasi-equilibrium response, it is dynamic and nonlinear and very much transient. So what I hypothesized was that we could gain some insight into the important causes or mechanisms of AA by looking at these different timescales. And what I found in my previous research is that Arctic amplification happens just a few months after you increase CO2 in climate models. In the plot on the right, the Arctic and the global average surface air temperature responses are in red and blue. And what you can see is on the x-axis, we have months since the quadrupling of CO2. By the third month, the Arctic surface air temperature response is sufficiently separate from the global average that you're able to detect significant Arctic amplification. And this was pretty surprising to see on such a relatively short time scale. In this research, I wanted to see how quickly does Arctic amplification when we increase CO2. My previous work, I only had access to monthly model output, but I really wanted to hone in on those shorter timescales. What mechanisms are causing that rapid response? And also, how does the time of year when we increase CO2 affect the resulting Arctic amplification? To do this, I used simulations from CESM. It's the Large Ensemble configuration. It's CSM version 1, and I generated 2-year-long fully coupled paired pre-industrial CO2 and 4x CO2 simulations. What that means is that I had a long control simulation, and I would randomly pick points in that control simulation. Starting from that point, I would run a 2-year-long integration with holding the CO2 at pre-industrial levels, and starting from the same point, another 2 years, but with an instantaneous quadrupling of the atmospheric CO2. I also perturbed the CO2 at 2 different times in the year. I had 100 members or pairs where I increased CO2 in January, and 50 members or pairs where I increased it in July. And I saved daily output from those simulations. Going forward, I define the Arctic as being from 70 to 90 north. And my main tool for investigating what is causing the amplification response is via atmospheric column energy budgets. Those will include terms like radiative feedbacks, which I calculated using CAM5 radiative kernels. If anyone's not familiar with kernels, they're pre-calculated radiative sensitivities that you can use to diagnose feedbacks in climate models. I calculated the atmospheric heat transport explicitly using the model output and quantified the ocean and in some aspects land effects as the surface heat uptake anomaly. It's very similar to what other studies have called their ocean term. What we found was that you can detect Arctic amplification just days after you increase CO2. In the January 4x CO2 simulations, Arctic amplification was actually significant the first day after you perturb the CO2 and remains statistically significant for most of the remaining 2 years. You can see in the plots on the left in the January 4x CO2 simulations, the Arctic surface air temperature response quickly separates from that of the global average. And when we look at the difference between the two, which is this black line, it's also opaque where the amplification is statistically significant. It's almost always opaque and always above 0. The July 4x CO2 simulations were a little bit different in that it took longer to kick up that Arctic amplification. It took about 25 days. Once you hit that point, it does remain significant for most of the remaining 2 years, but it was very surprising to see a detectable signal so soon after the radiative forcing is imposed. Given that this meeting is focused on ensembles, I wanted to provide a little context as to why I picked 100 ensemble members for the January 4 times CO2 and 50 for the July. And what I found is that the Arctic is very noisy in the winter. So here I have the same plots as the previous slide, but with varying ensemble sizes, just 10 in the first row, and then 25 and 50 and 100. And what you can see is that there is an incredible amount of noise, and it's very difficult to detect a signal if you only use, for example, 10 ensemble members. And once you increase that amount to 100, things tend to smooth out. In July, the Arctic is still relatively noisy, but less so than in January. So we found that we only required 50 to sufficiently beat down the noise and get some detectable signal in these simulations. Now, sea ice is often thought of as the dominant, most important cause factor in Arctic amplification. And I agree with that. However, on these ultra-fast timescales, that doesn't appear to be the case. Here I show the change in the sea ice area, the absolute change and the percent change in the January and July initializations. And what you can see is in the January initializations, where we have immediate day one amplification, there's very little change in sea ice area until you get to, say, the first spring and summer. In the July 4 times CO2 simulations, it took 25 days to get Arctic amplification, but we have this immediate decrease in sea ice area. That leads to a somewhat counterintuitive, but I think interesting conclusion that Arctic amplification actually developed in the simulations that don't have a rapid decrease in sea ice, faster than the simulations where there is a rapid decrease in sea ice. Now we'll look at some energy budgets of the atmosphere and the global average. While I did these for 2 years, I think the first month is probably the most interesting timescale to look at, and it's kind of what we define as the ultra-fast timescale. So I'm just going to show these energy budgets for the first month. These plots can be a lot to take in at once. So to orient ourselves, what I have here are the temperature contributions from various mechanisms. If you look here, it's the source albedo feedback, atmospheric heat transport, cloud feedbacks, surface heat uptake, Planck response, water vapor feedback, and the lapse rate feedback. The values here are the difference between the Arctic average and the global average. What that means is that values greater than 0 either warm the Arctic more or cool the Arctic less than the global average, thus can be thought of as contributing to Arctic amplification. Values less than 0 will be opposing Arctic amplification. When we look at just the first month of the January 4 times CO2 simulations, it's somewhat striking that the surface heat uptake response, this blue line here, appears to be a clear dominant factor in terms of what is causing this rapid Arctic amplification. There's also some contributions from the lapse rate feedback, but it's much smaller in the Planck feedback, which is an orange line just underneath the lapse rate. July has a very different story. You also start with an initially positive surface heat uptake response, but by the first week that becomes 0, and then actually opposes Arctic amplification on timescales after the first week. It appears that any amplification that does develop seems to be from the surface albedo feedback, which is consistent with those decreases in sea ice area that we saw a few slides ago. It was somewhat unexpected to see the surface heat uptake response play such a strong role on short timescales. So we broke up the surface heat uptake response, that blue line, into individual terms, which can be thought of as the surface energy budget. A lot of the lines here are the same as in the previous slide: surface albedo, cloud, water vapor. The temperature feedbacks at the surface are normally broken up into atmosphere and surface temperature components. And these last two terms, the FLH and the FSH, those are turbulent heat flux responses, LH being latent heat and SH being sensible heat. What we found was that throughout the first month of January 4 times CO2 and July 4 times CO2, you get this big pro-Arctic amplification contribution from the latent heat flux response. In the January simulations, you get a little bit of a contribution from the surface temperature too. Now, the reason that doesn't materialize as amplification in the first month of the July 4 times CO2 simulations is it appears to be compensated by the surface albedo feedback at the surface. It can be a little funny that the surface albedo was strongly positive on the last slide and negative here. It's just a matter of perspective. The surface albedo feedback is causing energy to leave the atmospheric column and go into the surface, potentially to be released later in the year through some other mechanism. But that effectively cancels out the surface heat uptake response and appears to cause the slower development of AA when you increase CO2 in July. To end with some points, we found that Arctic amplification develops immediately after you quadruple CO2 in January, before you have considerable sea ice loss. In July, Arctic amplification is a bit slower to develop despite having significant sea ice loss. It's clearly sensitive to the time of year that you increase CO2 on these very short ultrafast timescales. One perspective that's interesting to consider is that on these sub-monthly timescales, the change in the surface air temperature is very small. I've been calling them feedbacks throughout this talk, but we could potentially instead refer to them as rapid adjustments in a different framework. We found that the latent heat flux adjustment appears to contribute to Arctic amplification, and that has not been previously recognized. We do have a bit of a hypothesis as to why this happens that I can get into if anyone's interested. And lastly, some I guess good news from this is that the Arctic is clearly a very responsive climate. So hopefully any efforts that humans make to mitigate Arctic warming are rewarded shortly after. Thank you for listening, and this is all in a manuscript that I linked here.
Thanks very much, Tyler. Again, if you have questions, you can raise your hand, or you could enter a comment in the chat. Tyler, for clarification, in your first slide, you show the results of the 4 times CO2 experiments in the IPCC CMIP experiments.
Yes.
So those are often referenced, as you said, with monthly fields and at some time out. But do those outputs also contain daily values that can be accessed? How do those experiments differ from the experiments that you showed?
Yeah. So the CMIP5 output, in order to, I'm not 100% sure, there may be daily temperature output for some selection of models. However, if you want to dig a little bit deeper and do something like a radiative feedback analysis, you require a ton of variables that you are lucky if they even have for on monthly timescales. So at least when we did that work, we focused on monthly, and I looked at the full 150 years integrations of the 4 times CO2, but the opportunity to use CSM was, in SEMA 5, they only increase CO2 in January. There's some evidence that it's important to Arctic amplification, the season that you increase CO2. So this also gave us opportunity to try increasing CO2 in July.
Okay. And Wilbert, you have your hand raised.
Yes, very nice, Tyler.
Thank you.
I'd be very interested to hear what your thoughts are, how the latent heat responds in such a quick fashion with respect to an increase in carbon dioxide in the atmosphere.
Yeah, absolutely. So I think it's when you're considering this latent heat flux anomaly, it's helpful to change frameworks away from feedbacks and move more towards the rapid adjustment framework. When you increase CO2, the effect at the top of the atmospheric column and the surface are not the same, causing some radiative divergence in the column. Previous work has shown that that induces changes in the hydrological cycle and actually suppresses latent heat transfer from the ocean to the atmosphere. What our guess is that that's happening in these simulations, this suppression of the latent heat flux transfer from the surface to the atmosphere, but is maybe not happening in the Arctic. That previous work relies on kind of a global constraint on the hydrological cycle that causes it. It doesn't necessarily hold true for any specific area like the Arctic. So what we think is that's possibly the cause of that latent heat flux response.
Great, thank you.
Yep.
And any other questions for Tyler? I think Wilbur took my question.
So maybe I have a follow-up question on the latent heat impact. How do you think the latent heat release, because latent heat you have to release in the atmosphere to affect the temperature. What are the processes that could cause the amplified warming through clouds or water vapor effect or?
Yeah, that is an excellent question. I had someone who was more of a tropics person ask me basically the same question. I don't have a great answer to that. What we've you haven't been able to, I guess, more robustly kind of answer this question, but it could possibly have to do with the resulting change in convection, changing the temperature distribution throughout the atmospheric column. Again, I don't have a great answer to that.
Thank you.
So in a rapid warming scenario, does the full column warm, or is the warming focused in particular parts of the column, as you would see in a monthly or like IPCC scenarios of the 21st century, where the warming is focused on the surface?
Yeah, it is mainly in the Arctic, near the surface. I think below like 700 hectopascals. It was interesting to see that still happen in the January simulations where you don't really have much of a change in sea ice. But there's other factors like the lapse rate feedback that can help concentrate that warming closer to the surface.
Okay. And regarding the hydrologic cycle, then, did you happen to see an instantaneous impact on precipitation or other hydrologic variables then?
I actually never looked at precipitation, so I can't tell you.
Okay. All right. Very good. It's nearing the top of the hour. So I think we'll adjourn. I'd like to thank our speakers, Marika and Tyler, for their presentations today. Very good. So for announcements, we have a meeting next month for our group, which will be on sea ice data assimilation. We're still putting that meeting together, and so we'll have more information about that upcoming. Tony, are there any other announcements? Any other housekeeping?
Well, just wanted to thank everyone for your patience, but we did get that recording started, so that will go live tomorrow.
All right. Thanks for everyone for participating and joining us for our meeting. And thanks again to our speakers.
Yes,
We'll
thanks
see
very
you
much.
next time. Thanks.
Sure,
Everybody,
thank you.
thanks, Marika,
Bye-bye.
thank you.
Thank you.